Hello, aspiring Java developers. Welcome to our quick 5-minute whiteboard tutorial on a super important topic, Java Multithreading and Concurrency. I am so excited to guide you through this journey. Have you ever wondered how your computer can run multiple applications at the same time, or how a single application can perform several tasks simultaneously without freezing? Well, the magic behind that is multithreading. In this video, we will demystify what multithreading means in Java, why it is essential for modern applications, and how you can start implementing it in your own code. We will cover the core concepts, look at practical examples, and even discuss common pitfalls to avoid. By the end of this tutorial, you will have a solid foundational understanding of how to make your Java applications more efficient and responsive. So, grab your virtual pens and let us dive right in. Alright, let us start with the very first core concept, how to create threads in Java. A thread is essentially a lightweight, independent path of execution within a program. Think of it like having multiple workers in a factory, each doing a different part of the job simultaneously. In Java, the most common and recommended way to define a task that can be executed by a thread is by implementing the runnable interface. The runnable interface has just one method, run. This run method contains the code that the thread will execute. Once you have a class that implements runnable, you then create a thread object, passing your runnable instance to its constructor. This separates the task, the runnable, from the thread that executes it, the thread object, which is good for design flexibility. It is a very clean and powerful way to manage your concurrent tasks. Now that we know how to define a task using runnable, the next crucial step is to actually start and manage these threads. After creating a thread object, you call its start method. It is very important to remember to call start, not run. When you call start, Java creates a new execution thread and then calls the run method of your runnable on that new thread. If you mistakenly call run directly, the code will execute on the current thread, defeating the purpose of multithreading entirely. Threads also have a life cycle, moving through states like new, runnable, running, blocked, and terminated. For example, a thread might enter a blocked state if it is waiting for some input or a resource. You can also temporarily pause a thread using thread.sleep, which causes the current thread to pause its execution for a specified number of milliseconds. This is useful for simulating work or staggering operations. Let us put these concepts into practice with a simple, yet illustrative example, a concurrent counter. Imagine you have a shared variable, say count, and multiple threads are trying to increment this count simultaneously. Each thread will execute a task that increments the counter. Without proper handling, you might encounter unexpected results. Here, we define a counter class with an increment method. Then, in our main method, we create multiple thread objects, each running a task that calls increment many times. When these threads run concurrently, they all try to update the count variable. This example beautifully demonstrates how multiple threads can work on a shared resource, and it also sets the stage for understanding potential issues that can arise in multithreaded programming. As we saw with our concurrent counter example, Simply having multiple threads access a shared resource can lead to problems. This brings us to common mistakes, specifically what is known as a race condition. A race condition occurs when multiple threads try to access and modify the same shared resource simultaneously, and the final outcome depends on the unpredictable order in which these threads execute. Our simple counter without protection would likely produce an incorrect final count because threads might read the old value, increment it, and write it back, overwriting another thread's update. To solve this, Java provides the synchronized keyword. When you mark a method or a block of code as synchronized, only one thread can execute that code at any given time. This ensures that operations on shared data are atomic and consistent, preventing race conditions. It is a fundamental tool for ensuring thread safety in your applications. Wow, we have covered a lot in just 5 minutes. Let us quickly recap the key takeaways from today's session. We learned that Java multithreading allows your programs to perform multiple tasks concurrently, making them more responsive and efficient. We explored how to create threads using the runnable interface and the thread class, and the crucial difference between calling start and run. We also understood the basics of the thread lifecycle. Most importantly, we identified the challenge of race conditions when multiple threads access shared resources and discovered how the synchronized keyword provides a fundamental solution to ensure thread safety. Remember, practice is key to mastering these concepts. Try creating your own simple multi-threaded applications and experiment with synchronized blocks. If you found this tutorial helpful, please give it a thumbs up, share it with your friends, and do not forget to subscribe to our channel for more exciting Java programming lessons. Keep coding, and I will see you in the next video. Happy learning!